Okay, welcome back. We're working through the implementation of a linked list and an array list. Both of them are examples or implementations of abstract list data types, and the reason why we're building them is to test the performance of both of them. We've completed the construction of our linked list as well as writing tests for it, and now we want to implement a different way of creating an abstract list or an array list. An array list is going to use the same interface, but it's going to be built a different way, as we saw in the first video in this series. So let's go over to Eclipse and take a look at what we are working with there. All right, we're going to go ahead and create a new class, which is going to be our Arraylist class. Now again, we're using the words that Java uses, but we're actually creating our own version of these. We're not creating the Java version of Arraylist. We're creating a version of list and array list that are impoverished versions of the Java version of them. Nonetheless, they demonstrate the architectural differences. So we're going to create a new class called Arraylist, and it is going to use the interface of list that we created as well. When we build that out, we'll see that we get a stubbed out file with all the components of our array list there. And I'll go ahead and add some Java doc describing what it is that our array list is supposed to do. All right. Well, we need to go ahead and we need to create all the elements. We need to create all the functionality for our array list. Our array list is going to be implemented differently though. We're going to have a primitive array underneath our data within our class that is going to grow as we need more data. So we'll start by creating that holder, that container that's going to have the data that's going to be our list for our array list. We'll call that data. It'll be an array of objects. Because we're going to allocate these at a given time, the amount of data that we have, the size of our array at any given moment is going to be our capacity. That's going to be how many items we can store, but the actual number of items that are stored at a given moment are going to be size, stored in the variable size. The idea here is that as size grows large enough, capacity will have to be increased as well. So that's where we're going to start. The next thing that we're going to need is we're going to need something that's a constructor that initializes these things appropriately so that we have default behavior that we expect. So let's drop that in here. Creating a new array list means that our capacity is going to be equal to 1. Currently, data doesn't have any capacity associated with it, so we need to create a new array which is of size capacity, or 1. Our size is going to be equal to 0. So the next element that we're going to add is going to go into index 0. We also have no data there, so our size is 0. All right, that is good enough for creating our initial array. And now let's talk about getting first. Well, when we have an array list, getting the first is really easy. All we have to do is make sure that we have the appropriate amount of data available to us. And then if we do have the appropriate amount of data, we just need to return the first element of our list. Because this is an array, it turns out that that's pretty straightforward. We simply say get first, and if our size is equal to 0, then we have nothing in it, and we throw a no such element exception. If we do have data in it, we just say the data from the beginning is just index 0. So we just return data sub 0. Easy enough. Likewise, if we are trying to get the last element in our list, it is a similar process that's also very easy. Instead of returning data sub 0 though, we're going to return the last element in our array. Now the last element in our array, the last element that we have is not the capacity, the element at capacity minus 1, because we may not actually have that number of elements stored. Instead, it's going to be the actual number of elements that we have stored minus 1, provided we have some present. So if we have one element in the data, then our last element is going to be data sub 0. Adding first, adding last, removing first, and removing last consist of shifting all of the data that's in our array up or down 1 and making sure that you just keep track of the appropriate indices along the way. So let's start by removing our first element. Removing our first element means we need to have a loop that's going to walk over all the elements of our array and move them left 1 space. All right, so first of all, if we have nothing in our array, then we have a problem. And we're going to go ahead and say no such element exception. But if we do have data in our array. Then we'll store the data that we're about to remove in a local variable called element by calling get first. And then we'll slide everything down. We'll say, have a loop that goes from 0 to size minus 1, and we'll say data sub I equals data I plus 1, shifting everything down to the left. Then the very last thing we do is we reduce the number of things that we're keeping track of, and we reduce size by 1. So size now equals size minus 1. Removing the first element is pretty easy. Removing the last element is even easier because of the way we keep track of things in our, let's see, where's remove last? Did I get rid of remove last accidentally? Drop that in there. Okay. Removing last is even easier because you don't have to shift anything down. Removing last, you just have to make sure that something is in your array to start with. You go ahead and get the element at the end of your array, or data sub size minus 1, and then you just reduce size by 1. You're no longer keeping track of the thing at the end of your array. The data is technically still there, but because the amount of data that you're keeping track of has reduced by 1, you'll overwrite it the next time you add something. Finally, you'll return that element. Adding something to the beginning and adding something to the end is a parallel kind of construction, except that you're shifting things to the right instead of shifting things to the left. So let's take a look at adding first. Now the one thing that's different about adding first and adding last is we have this problem of our capacity. If our capacity gets overrun, then we're going to have to do something to increase our capacity. And that's the one thing that's different about adding first and adding last. So I'm going to assume that we have a helper method called check capacity. And what check capacity is going to do for us is it's going to see whether or not we have space in the array that we have allocated in order for this new element that we want to add to the beginning to be present. And if we don't, then check capacity is also going to increase the amount of space that we have available to us. So let's just assume for now that we have this written, and after line 91 we have enough space to add something to our array. So we just need to slide everything up 1. We take everything from size, we're going to do a loop that goes down. We say size all the way down to element 0, going from highest to lowest. We'll shift everything from 1 position to 1 position up, leaving the element at data sub 0 with space where we can put the new element that we want to add to our array list. We'll increase the size of the elements that we're keeping track of by 1, and we're all done. Now what does check capacity actually have to do? Well, check capacity has to see whether or not the size, or the number of things that we're keeping track of, has grown too large, grown larger than capacity. If size has grown larger than capacity, then we need to create a new array. And this new data array is going to be twice as large as the previous one. Once we allocate that memory, we need to copy everything over. So we go from 0 to size and say new data equals what was in the old data. And then we cause the reference data that was pointing to the old data to point to the new data, and we're going to double the size of the capacity. Size remains the same. It's just that we have a bigger underlying array that's keeping track of this data. All right, so that added something to the beginning. Well, we also need to add something, have a method that will add something to the end. Just like removing something from the end was easy, so is adding something to the end. We can do that simply by first checking capacity. If we have enough capacity, then data sub size, or the position at the end of the array where we're putting our new elements, is going to get our new element, and we increase our size by 1 so that we don't overwrite that element again. Boom, adding our last is all done. So those are the basic elements that we needed in our array list without using an iterator. We have the added benefit of being able to return size very quickly. Size in an array list is very trivial. We don't actually need an iterator to implement size in an array list. We just return the internal variable size that's keeping track of how many elements we have. Likewise, get doesn't need an iterator either. Get, because we have random access just by indexing any element of our data array that we want, we can just say get with whatever index we're looking for. If our index is negative, we throw an exception. If our index is too large, we throw an exception. Otherwise, we just return the data located at that position. Because it's an underlying array, we can use this random access procedure in order to get our data. All right, nonetheless, part of what we are building has to conform to the list interface, which means that even though it's easy to do things with our array, we still need to implement an iterator. So we're going to need to implement an iterator. We'll do that in our next video segment. And the thing that we're going to return in getIterator will be a new ArrayList iterator. And that ArrayList iterator will need to be implemented. We'll implement it up here as an internal class as well, just like we did with the linked list iterator. So we will have a private class ArrayList iterator, which implements the interface list iterator. What do we need to implement here? We need to implement each of these different abstract methods. We'll take a look at that in our next video. Thank you for your attention.